right? And only if the magnetic field is changing, either because I'm moving in and out of magnetic field, or because I'm moving in and out of magnetic field, will this appear. Alright? So it's the change in the magnetic field flux what makes the current in this current appear. Alright, so let me see if I can read this. There is an induced current in a conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current will produce an induced magnetic field that opposes the change in the flux. Alright? So the direction of the current. So there's an induced current, and this induced current, of course, produces a magnetic field. This magnetic field is the direction, and therefore the current, the induced current produces a magnetic field. So this magnetic field is the result of fighting this change. So Lenz's law opposes the change in the flux. I'm getting a sugar bowl, and that's probably my juice. I hope it's not horrible. I don't know. It looks horrible. But I already stopped the pot. I already took apple juice. Somebody has a phone. I don't think anything bad will happen, but you never know. I've never had that. Apple now. Just in case. If we have a changing flux, magnetic flux through a loop, you will have an induced current. Lenz's law tells you the direction of this current, because the current induced is such that it will oppose the changing flux. It will induce this current that is induced will obviously create a magnetic field. Okay, a current induces a magnetic field. You have a current, there's a magnetic field. Because it's an induced current, it's an induced magnetic field. And it will oppose the magnetic flux that it initially generated it. Okay? And it opposes this opposition. This opposition to change is what we call Lenz's law. So let's see, probably this is a good time for a demo. Think of a metallic tube like this as a continuous of a solenoid. Many little loops, right? You can see that? I could have like a many coils, or a continuum of or basically this metal tube would be a continuum of coils. Alright, so I should make it stand in a stand. And the coils have no magnetic field through them, so there's no flux. So they're happy to be where they are, right? That's their state. And if there is a change in flux, they will fight it. Right? Guys, can you see on that side? Try to be as centric as possible, okay? Yes? Right. One of these balls, they seem identical, is a magnet. We don't know which one it is. All right? But if there is a magnetic field, if I put a magnet through this, all right, as it moves, as gravity pulls it down, it will be changing the magnetic flux through those infinitely tight loops, right? And they will fight this flux by creating a current, all right, that will oppose that change in flux. All right, so a change in magnetic field. So it had no so if the flux is magnetic field going this way, magnetic flux going this way, the current created would create a magnetic flux that opposes it, or a magnetic field that opposes that, right? Going up. Now if there's a current in the induced current, right, and there's magnetic field, it will be a force on it, right, that opposes that and will definitely shut it up. So let me ask you which one. If that is not happening, so let's see. If that is not happening, a ball will just fall down, right?
Is that the magnet? Because I heard that.
I don't know. Let's see.
That wouldn't demagnetize it, would it?
Right now I cannot see an effect, right? One is a magnet, one is not. If there are no coils around it, there's no change.
I heard that like by hitting a magnet very hard, you can actually demagnetize it.
Do you think I've now ruined the demo? Maybe, right? Maybe.
You probably did.
We'll see. So one of these two is a magnet, unless I've demagnetized it by hitting it hard. We'll see. So let's see. Now these are coils. That looks the same to me. Is it the same? We'll see what happens if this is a magnet, then all right. Oh, yes, this is a magnet. I didn't demagnetize it. All right. So yes, nature is fighting, right? The tube is fighting that. Thank you so much. It's fighting that. All right. Again. Falling, but it's fighting that it eventually loses.
Is that an neodymium magnet?
I don't know what type of magnet it is, but pretty strong, and I didn't destroy it.
Mm-hmm.
I didn't don't ask me now, because I'm actually not. I'm fragile right now with this sugar issue. All right.
I think it might be a neodymium magnet.
The magnetic field is exerting a force on the little infinite loops, right? It's changing a flux. So the magnetic, it's like a magnet, it's this situation. All right? I have a falling magnet with a north-south, all right? So it's changing them. Initially, the loops, the infinitely tight loops, don't have a magnetic field. Suddenly I drop in a magnet, all right? And of course it will induce, because there's a magnetic flux, it will induce a current, all right? This current now induces a magnetic field, which is opposing the original magnetic field. So if there was north going this way, there will be north going opposite, all right? Telling me that I have going for a load. I'm already taking some precautions. We'll see. I don't know what to do beyond, more apple. Okay. So that was one. Because I'm changing the flux, and there was no flux initially, will create a magnetic field to fight that, right? So if the north was going down, it will create a north going up, and therefore it will take longer because it's now subject to a magnetic force, and that's what happened. The other thing that you said, I asked you this question. If I have a magnetic field, and I change and I rotate a coil, there will be a flux change through that coil. As a result, I'm going to be creating a current, an induced current. Well, this little thing is a magnet that is connected to a loop, and by changing that loop, I'm creating current. All right? And that's how you generate electricity, in fact. All right? There is a loop that is turned by turbines, waterfall falling down. It turns those loops, and as a result of that, I have an induced current and I have electricity. That's how you generate electricity. This is a generator.
What about solar panels?
Solar panels are a little different, but that is indeed, this is not the solar panel technology. This is clean energy, right?
Mm-hmm.
Well, you give me an apple and I'll turn it forever, right? Or waterfalls are clean water, clean energy, right? Solar, anything that turns it, well, if you have a turbine, meaning a coil turning, or the handle being turned by a motor, a gasoline motor, well, that's not very clean. But you can get it off of wind turning, you can get it off of waterfall turning turbines, and you get electricity. So this effect that we're studying is what moves our economy. We need electricity. Then we have another little device. This one will be changing the flux. This is a changing magnetic field, up and down, up and down, up and down, right? And this thing will fight the change. Hopefully I haven't broken the demo. All right? And again, there will be induced currents in this infinitely tiled coil system. All right? So what do you think is going to happen? Exactly, it's going to go up. Let's see if it's true. Okay, I said I'm not feeling that wonderful. I was going to catch it. That was my original plan, but then it hit my head. Okay. So this one has less coils, right? So should it be equally high or less high? Less high. Let's try that. Yes, didn't hit the wall, the ceiling, so that was indeed less. What about this one? What does it have? So what happens there? What do you think will happen? Why? There's no loop, so current cannot go through, so that there's indeed a short, basically. So even though there's a flux through that imaginary area, there's no loop, so current cannot go through. No. Okay. Of course, equivalent to this, instead of I have some electrical wiring, so that will change. Oh my God, change the. And of course, if I put this here, sorry, I'm battling with everything right now. We will light the bulb, of course. Okay, yes? Because there's a changing magnetic field here. All right, those were the toys I brought with me. All right, so let's see where we were. Lenz's law, so it opposes, okay? The magnetic field through the loop changes, the loop changes in area or angle, the loop moves in and out of magnetic field. All these three cases have an induced current because the external magnetic flux is changing. The current generates its own magnetic field. It is this induced field that opposes the flux change, okay? So, of course, when there's no flux changing, there's no current, but as soon as I go in or out, we will have an induced magnetic field due to this current being induced. So here are the questions, all right? So as you can see, in the first case, the magnet is going down, so north is going into the loop, right? As I lower the magnet, more north is going through that loop, the more magnetic field is going through. So the loop will fight that to create, it didn't have anything initially, or it had a weak magnetic field, so as it gets stronger, it tries tries to fight it by creating an opposing magnetic field to cancel it out. How can it do that? By creating a current that goes in this direction, which if I look at the loop from above, it would be a counterclockwise direction, right? If I look at it from above, I need a magnetic field that goes up. So that's the direction it's going to create. If I move now I have a magnet in the loop, right? And I start to move it away. So now I was happy with having magnetic field. It's going to start to lose it. So, oh no, I cannot lose magnetic field. So it creates magnetic field in the direction that it had it to compensate for that loss. All right. So that is another reaction to what it had, and now it's going to change it. It's changing by the fact that I'm moving away, and the current is there to react to that change, right? In this case, it's losing it, so it wants to add magnetic field. In this case, it's adding magnetic field, so it wants to subtract the addition of magnetic field. So here we go. I think these are these questions? Yes, quick check. All right. Motion of magnets causes increasing downward flux through the loop. All right. If you move away, just okay. So we did the case, these two cases. All right. Obviously, you have these other two cases where you invert the magnet, right? If you are decreasing south field in this direction and you're moving it away, it wants to create magnetic field in the direction that's being lost. So again, if you look at it from above, it would be counterclockwise. And if the south pole is coming in, okay, so you have excess magnetic field pointing that way, so you want to create a magnetic field that opposes that, so therefore the current will be going clockwise. So I think we have a quick check. In which direction is the induced current? Clockwise or anti-clockwise? I'm going to have another bite of the apple. What do you think? Who says clockwise? Is the flux increasing or decreasing?
Increasing.
Increasing. So there's more and more magnetic field going into the board. So what would the loop want to do? Decrease it. So point in this direction. So it will be counterclockwise. Right? Counterclockwise. Okay. Quick check. A bar magnet sits inside a coil, okay, that is connected to a meter of some sort. For which of the following circumstances, what can you say about the current in the meter? The bar magnet is at rest in the coil. Is it current to the left, to the right, or no current in the meter? No current, that's right. Oh, sorry. The bar magnet is pulled out of the coil. All right? Now, let's say that the south end, I grab the south end and I pull it out. All right? So, it's losing north, right? It's losing north, so it wants to create north. So how does it create north? All right? By having a current go this way, right? So the current goes that way, goes from left to right, no? Because if it goes this way, it rolls like that, and of course the magnetic field is in this direction. The bar magnet is completely out of the coil and at rest. That's right. I see one hand that told me 0, so I'll take that as everybody's thinking that. Yes, no current. The bar magnet is reinserted into the coil. So it wants to create a magnetic field in this direction, right? So the current has to go this way. It has to go this way, right? So the current has to go from right to left, right? Another quick check. A bar magnet is pushed towards the center of the wire of this loop. Which is true looking at the loop from above. There is a clockwise induced current, there is a counterclockwise current, there is no current. A, B, or C? Looking at it from above. Who says A? Who says
Wait,
B?
clockwise. Wait, are you looking at it from the top or the bottom?
Yes, of course you're looking at it. Well, that's what this says.
Okay. Oh yeah, I don't really say that.
So A? A. Who says B? Who says C? So 80% of you have no opinion, by the way.
Right. Okay. I think it is clockwise as viewed from the top.
Exactly, it is clockwise from view from above. Who has a question? Who doesn't understand why? Yes. Because it wants to cancel that magnetic field. Because it's this, by bringing the magnet closer, the lines are going out of the north, right? Out of the north, and more lines are going through that loop. Right, magnetic field lines. So therefore, thank you for clarifying. Yes, so the more and more magnetic field lines are going through that loop as I approach with the north. So the loop wants to cancel that. How do you cancel it? You need to make a magnetic field in the opposite direction. So the current has to go this way, and if you look at it from above, that means a clockwise direction of the current. Yes? All right. Example, a loop is moved towards a current carrying wire as shown in the figure below. As the wire is moving, is there a clockwise current on the loop or a counterclockwise current or no current?
Counterclockwise?
So the flux is increasing or decreasing? As the loop approaches the wire, is the magnetic field flux, i.e. how much magnetic field is going through the loop, is it increasing or decreasing? Increasing. So the loop has to fight that increase of magnetic field. In which direction is the magnetic field due to the wire? Into the loop. So it has to fight that in. So it has to create a magnetic field going out. So which is the direction of the current? Counterclockwise. Okay? Okay. Means we must create a magnetic field out of the page and therefore counterclockwise.